And Nikita, what's meant by diffusion? What's the property of diffusion?
Hides the relationship between the key and the cipher.
Good answer, but it's the wrong answer.
And the output.
Okay. Let me get the. Okay. What size is the key in Dell's system? Dell's cipher system. What size is the key? 64 bytes. 64 bits. Are you sure? Okay, so it's 64 and then reduced. Why is it reduced, or how much is it reduced by? So when you start encryption or decryption using DES, we give it 50 or 64 bits. They are immediately reduced. Which parts of the bits are reduced, or how much? It's a reduction. 8 bits are reduced. Which 8 bits do you know?
30, 0 to 30.
The parity bits. Do you know what numbers are the parity bits? Which bit is the parity bit in this system? In any system? Which bits are the parity bits? No. We have 8 bytes, we give it 8 bytes, and then we remove the parity bits from the bytes. Where is the parity bit? Which bit is the parity bit? Pardon? Okay. It's the last bit in every byte, so it's bit number 8, 16, 24, 32. So every 8 bit, but they're numbered, we know the exact position of the bits. Let me get the attendance going. What's the basic idea, guys, of DES? Who can tell us a little bit about DES? How does it work? What's the basic operation of DES? What's the basic operation of DES? What functions are used? Is it a substitution? This is what I want to know. Is DES encryption? Is it a substitution system or transposition system? Okay, you know, is DES a substitution or transposition? Pardon? Transposition is a good answer, but it's not. The right answer. Is it transposition or substitution? Substitution is another good answer. Wrong answer as well. Hold on, I have a volunteer here. But is it substitution? It is. Or is it transposition? Oh, both. Yeah, it's both. It actually does substitution and then transposition, and then repeats that 16 times. And that's how it works. It does a transposition and a substitution. And it does that a number of times, which is 16 times based on the key. So first, you take the key and they generate 16 keys. Anybody knows how are those 16 keys generated out of DES's key? Anybody has any idea? Anybody wants to have, if I start and I say, okay, the key, which is, how big first is the key? Can you remind me, how big is the key? 56 bits, exactly. We start with 64, but we get rid of 8 of the bits, so we have 56. It's first split into 2 halves, left and right. And then, what's the next step? Anybody remembers the next step? Each half is shifted to the right, 1 bit or 2 bits. I think it's a circular shift, so it doesn't change in size. And then join them, and that's key number 1. And we keep the 2 halves, shift them again, and join them, make key number 2, and shift them again. So that's how the basic operation is. You take the key, the 64, remove the 8, you have 56, split it into 2 halves. Now, you keep the 2 halves. It's just every time you take a copy, shift them, and that's a key. Join them. Shift them to the right, you get different halves, even though they're the same size. They're the same, it's just rotating the bits. And then join them, and that's another key, but keep the same 2 halves and keep shifting, and each time you shift, you join and give the key, and you do that 16 times. What about the encryption part? Even in the encryption part, we take the data. Let me just start this so we don't forget. So that has started. How does DES encryption work? You get the 64-bit block of data, so it's a block cipher. It's not a stream cipher. So if you need to encrypt a message or a file, you open the file, you take 8 bytes, which is 64 bits, split them into 2 halves. There are a couple of operations. First, we kind of do a permutation, that's transposition, change the position of the characters, and then split it into 2 halves and work in one of the halves. Only work on the right half and then swap the halves, and then work on the right half again and swap them, and you do that 16 times. And somehow that makes it, if you repeat it again, you will reverse the operation somehow. What's the avalanche property in an encryption system?
It is whereby a small change in the ciphertext results. A small change in plain text results to a huge change in the ciphertext.
Start it again, say it again.
Avalanche effect is whereby in case of a small change in the ciphertext.
A small change in the plain text will result in a big change in the ciphertext. So it makes it difficult for people to attack it by just saying, okay, let's change 1 bit and let's see. If you change 1 bit, it'll probably change half of that ciphered message. Oh, this one is the one that doesn't work. So I think we got the general basic idea of DES. Did we? Right, so let's look at the details of how does actually DES work. So we know the general idea. If you need to program it, maybe it's good to have a look at this, because it'll give you bit by bit what should happen, and that will increase your understanding of DES. So first, DES was issued in 1973 on the National Bureau of Standards, published the notice for Federal Register, a proposal for a cryptographic system, but let me get straight into the operation. So it's 1974. The submission was made in 1977. DES was in operation. So DES works on bits or binary numbers, and each group of 4 bits make up a hexadecimal number. So it deals with hexadecimal numbers when it's looking at the bytes. DES works by encrypting a group of bits or blocks of 64-bit messages. So it takes 64 bits each time of a message to encrypt it. And this is the same as the 16 hexadecimal numbers. Doesn't matter, we look at the bits only. And to do the encryption, DES uses keys. So there's a key, and the key starts at 64-bit key as well. DES was known as the 64 kind of encryption system, because the block is 64, the key starts at 64. And however, the 8th bit in every byte is ignored or removed. So in the DES algorithm, so that the effective key size is actually 56-bit key. But normally we feed it with 64 bits. But in any case, 64 bits or 16 hexadecimal digits is the round number upon which DES was organized. So DES was organized on 64 bits and 16 loops and so on. So, for example, the plain text message, this message, whatever it is, 878787 in hexadecimal numbers, can be encrypted using a key, and you end up with the 00. This is an unusual kind of encryption and decryption system. Just this particular message. The ciphertext is decrypted with the safe secret key, and the result is, so if we use the same key in the middle there and decrypt this message, you'll get back that number there, 7878. So it's a symmetric, basically it's a symmetric system that has a plain text message fed into the encryption algorithm, and a key is used, and both they generate a ciphered message. That's not shown here, but that's the one that's sent to the receiver. The receiver uses the ciphertext message and the key, and should generate back the plain text message. So a symmetric system, it has a problem of key distribution like every other symmetric system. But this system is kind of the foundation of, the next 2 generations. So we take an example of a message, and it's going to be encrypted using a particular key, so it goes straight to it. The plain text message is translated, this message there, that's the only message I found, translated into that hexadecimal number, which I'll just look at it in binary, and we're going to be using a key. I don't know where the key is. So the message is padded with zeros. If the message is not 64 bits, it has to be padded with zeros at the end. So because we only work with 64, a block of 64 bits. So if the message is encrypted using this particular key, this is the key at the end there, we get the following cipher message. There's the cipher message. And this is the secret code that can be transmitted or stored. So that's the encrypted message there. Decrypting the cipher message will bring back the original message in English. So, we want to see how it actually happens. What happens inside DES now? DES is a block cipher, meaning it operates on plain text blocks of given size 64 bits, and returns also a ciphered text block of the same size. So when you encrypt a message, it doesn't change in size. It just changes the content, but still the same size. Every block is 64 bits, that's 8 bytes. So DES results in permutation among the 2 to the power of 64 possible arrangements of 64 bits, each of which may be either 0 or 1. So it's because they're all zeros and ones, it will generate another message with basic possible permutation of 2 to the power 64. Each block of 64 is divided into 2 blocks, 32. So the message is split into 2 halves, left and right. And this division is only used in certain operations. But here's the example. Let's look at an example I'm following. The M message, it's in hexadecimal, but we look at it in binary. So if you are like writing this, this is the message to start with that we want to encrypt. So what we do is split it in halves, 2 halves. Instead of 64, we'll have 32 left half and 32 right half. The keys are actually stored as being 64-bit long as well. The keys are 64-bit long key. But the 8th bit and the 16th bit and 24th bit and 32nd bit are removed. Nevertheless, the bits are numbered from 164. But the 8 bits just mentioned get eliminated inside the system. So here's the key written in hexadecimal, but this is the real key, exact real key in binary. Now, let's create the keys first and then let's encrypt the message. So this part now we're going to do is that creating the 16 keys, how the 16 keys are generated. Remember, the 16 key, you take one key, that's the 64-bit key, split it into the 56-bit key, it's split into 2 halves, shift and join together to become a key, and then shift, join together. And even the shifting, the protocol, the standard tells you how many bits you shift for each time. We're going to be doing this 16 times. And the protocol specifies in the first, second, and third iteration, maybe there's 1 bit shift. In such and such iteration, it's 2-bit shift. So to create the 64-bit keys, the key is permutated according to the following permutation. This is a PC permutation. Anybody knows what P and C stand for?
Permutation, combination.
Pardon?
Permutation.
Yes, P is for permutation. That means we're going to mix the bits around. And C?
Combination. Combination.
No. Condensation.
Condensation.
So it's permutation, condensation function. And my condensation is going to reduce the key. The key is 64, we're going to reduce it to 56. And so you automatically, you know already the bits they're going to be condensed, so we get rid of. So that's the first permutation. That's the first thing we do to the key. So we put it through a permutation condensation function. Since the first entry of the key 57, this means that 57th bit of the original key, becomes the first. Yeah, this is the way to read the tables. Now, this table is in the standard. So what you do is you write the key 1, 2, 3, 4, 5, 6, 7 bits, 1, 2, 3, 4, 5, 6, 7, 8, 56 bit. So this table bring the 57 bit here. So the bit number 57 is brought as being the first one. This one is the bit number 4, bring bit 49. That's how it works. So this, just to show the programmers what we want to do. You have a key that has from 1 to 64, go and bring bit number 60, put it there, put number 21, put it here. Here, that means the positions are in 57, that's position 1. So position 1, bring bit number 57, put in position 1. In position 2, you bring bit number 49. In position 3, bring bit 41, and so on. So this is, first you mix them up, this is the permutation, but also if you notice, there'll be no mention of number 8 or 16 or 24, we ignore those bits. So we only bring, that's bit number 1, I don't know where number 2 is, that's 3, 4, 7, but there's no 8, there's no 16 number. So that's basically, we're just picking up all the bits except number 8, 16, 24, 32, and so on. So this permutation means change the position. Condensation means get rid of some of the bits. We reduce the size from 64 into this one here, which is 56. So that's the first thing that happens to the key. So if you do, you probably won't, but if you do implement coding or DES, that's the first function. You say, okay, run this permutation. So you look at the key, every bit number 1, put it there in that position and so on, and now you have a smaller key. You have an array, you have another array with the key with the reduced number. This is, if you want to see it, this is really what we did. We brought bit number 1, we put it here in position number 8. But when we brought number 2, 3, 4, but see, as you can see here, bit number 8 is gone, it was not used. See, bit number 8, bit number 16, 24, 32, we just left it. We pulled every other bit, but not those bits here. So that's what we get. We get a smaller key, and it's mixed up as well. Even though the mix-up is already standardized, so we always do the same permutation. So if we do that correctly, and if you do program it, for example, and find you've done it correctly, that's what you get. That's the key we started with, this is the key we got. If you want to follow it, difficult to follow it with the parity. But this is a 56-bit key. Now, all we have to do, the next step is split the key into 2 halves. They call it C and D. They didn't want to call them left and right, just because we are splitting the data into left and right. Now, this is each half. This is the half that we're going to shift, or to the left, I think it's left shift. We do them, so that means if we do shifting to the left, we bring that 1 into that there. And same with this one here. Shifting that 0, I go there. If we're shifting left, depending on where we are shifting left or right. So, we're shifting to the left. We now create a 16 block of C's, lefts and rights, or C's and D's. And each one is generated from the one before it. And we do a left shift. And the shift is circular left shift. Circular, that means you take the bit from here and put it the other way. So this is exactly what we are going to be doing. We've already done this bit here, the blue part we've already done. We permutated a key and we condensed it into a smaller size. Now it's 56. We split it into two halves, C and a D, or left and right, if you want to call them left and right. And so we have 28 on each side. 28 bits on this half and 28 bits on this half. Shift them to the left and join them, and that becomes, okay, and join them and pass them through a second permutation condensation table. So we have a second table that will further reduce. Remember, we join them together. We have 28, do a shift, join them together, they're 56 again, put them into this permutation, reduce them to 48. So the keys that actually we produce are 48. So the keys first reduced from 64 to 56, and then each key is reduced to 48. But remember, the two halves are still 28 each. So we go to the next half, the next key. So we shift the keys to produce the first key, but we go down again. After shifting the keys, we shift them again and join them together again after passing them through a permutation, and that would reduce them again to 48. That's key number 2, key 3, 4, 16. So this is exactly what happens. So in fact, if you need to know the summary of creating keys, they're asked how are the 16 keys are generated. You say, okay, we start with the main key, pass it through a permutation condensation table, it will reduce it from 64 to 56. Then that 56 is split into two halves. Now we're going to repeat this 16 times. Shift the two halves to the left, 1 bit or 2 bit. And after every shift, join them, put them together, and pass them through another further permutation and condensation table. So they're reduced again to 48. So the 16 keys we're going to have, each one of them is 48 bits. That's the summary. Now, this is what the protocol says. You're going to do this 16 times, 16 iterations. This is how many bits you shift them to the left. You shift them once, 1 bit, or 2 bits. I don't know why they do that, but I guess it makes it a bit more difficult. It makes them better keys. But okay, you won't be asked, hey, which the 4th one or the 16th one, is it 1 bit or 2 bits? That's not the kind of question you ask. But you ask the general steps. You need to know the general steps. Okay? But just to let you know, this is there. But you must know that there is a left shift. Shift to the left. Whether it's 1 bit or 2 bits, we won't know. But if you are programming it, you need to do exactly how many bits you shift to the left. All right, this means, for example, C3 and D3 are obtained from C2 and D2. So every key is obtained from the key before it, from the two halves before it. And all shifts, those shifts are all circular shifts. If you need to know, here's the exact halves. You don't need to know or remember, but if you are programming it, it's handy to have it. So first, these are the two halves. You do a shift to the left, so that one there should travel there. So it happens here. See, from C0 to C1. You see, this one had 4 ones, only 3 ones, because that one, the 4th one, is gone to this side. So that used to have 4 ones at the end. Now it has 5 ones. The second half, or the right half, if you want to call it right or left, it has 1 0 on the left. Now the 0 is gone. Because we took that 0, we moved it all the way around to this side. So it went to this side. So just so you know, this is real shifting, it's happening. And maybe the third or fourth, it has 2 bits shifted, so you'll be able to notice them if you want to be very accurate with them. But this is correct, it's been checked many times. So these are the 16 keys that we have now. And each one of those, these are the 16 halves. You need to join them together to make the key. Join them and reduce them. Because now each one of those, I don't know, it's 26 and 26, that's 50, or 28 and 28, 56, but they need to be reduced to 48. And that's by the second permutation condensation table. This is the second table that will reduce the key both from 56 to 48. So the outcome of this is a key of 48 bits. This just tells you exactly what this table does. Maybe it's better to look at it directly. This 14, what does 14 mean here? Bring bit number 14 from the key and bring it to this location number 1. This is location number 2, bring bit 17 from location 7, and so on. And this one, this is bit 5, means bring bit number 1 and put it here from the original key. So that's how it works. Again, I don't know what numbers are missing here. Should they be 8? I don't know if they should be 8. Anyway, it's missing some numbers. If you want to know exactly which numbers are missing, you can look at those. And, sorry. No, the ones that are missing is 9, 18, 25. This is what the standard says. This is not necessarily, because they're not really the parity bits we're getting rid of. There are no more parity bits. Okay, so that's basically how the keys are generated. Now each key is put together and reduced in size, and here are now the keys. These are the 16 keys. Each one of these keys is 48 bits long. The data will be later on XORed with 48 bits of data. But anyway, so that's one step is gone. This is one part of DES, is that you need to generate the 16 keys. So have a general understanding. You might be asked, how are the keys generated? You don't have to give an example, but you need to explain the situation. So it's permutation condensation first. Split the key into 2 halves, shift and join, and then each key is further reduced, condensed, of 4 or 5 steps. Now let's get to the other part. We have the keys. Now let's encrypt. How does DES encrypt or decrypt? Again, with the data, it has an initial permutation. So first we take a block of data. Remember, the data, you don't get rid of 8 bits because it's not a number, it's not the key. This is the data we want to encrypt. So first take that message and IP it. That's initial permutation. That means first thing we do a transposition. Change the position of all the bits. This rearranges the bits according to the following table. So there's a table as well. So the key doesn't go into this. So all data happens, same thing happens to all data, same permutation. And the entries in the table show the new position. Okay, so let's look at this table. So this is the first table. This is what happens to the data first. We do a permutation. Let's just change the position of the bits in the 64 bits data block. It's an 8 byte, and each byte has 8 bits. And this is what happens to the actual data. So So this is the original message that we got in binary, and this is after the permutation according to that table. You're going to see exactly if this is made according to the table. Oh. Okay, let's look at this bit here at the top. 1, 2, 3, 4, 5, 6, 7, 8. Bit number 8 here. It says, bring me the bit from position number 2. So this is position number 2, is a 0, and we want to put it in position 8. So that bit actually, in position 2, went to position number 8, according to this one here. This one is position, this is from the 4th bit, bring it to position number 16. 1, 2, 3, 4, 5, 6, 7, 8, 16. So if we go down here, position 16, you'll find the original bit. But trust me, it's correct. It's been checked before. So this is actually what happens. So it's, for you, you don't need to remember this. What you need to remember is that there's a permutation. First thing we do to the data is permutate it. You're not asked to remember any of the stuff, because that table isn't the international standards. If you're a programmer, you get that table. All you have to do is follow it. But this is just an example of what to expect if you follow it. Right, and then we split the message into 2 halves. So remember, we started with a message that's 64 bits. We split it into left half and right half. Each half is 32 bits. Remember, the key is 48. Each key that we're going to be using 48. And we only operate in one of the halves. So even whichever half we'll be working on, let's say the right half, for example, the right half is only 32 bits. We need to expand it to make it 48 like the key. And so when we XOR them, each bit will meet another bit and they'll give us a result. Okay, so just to expect. So now, we split this into 2 halves. Each half is 32. We're going to work in one half. We're going to do something to the half to make it a little bit bigger. But anyway. So now the 16 iterations, this is what we're going to do 16 times. We're going to swap. The new left half is going to be this previous right half. So every time we finish, we take the right half, make it the new left half, and we take the right half becomes, we take the left half, operate on it, and becomes our new right half. So we will be doing all the work only on our right half, and then OR it with the left half to make the new right half. So, again, this is overall. If you are asked to describe, maybe this is something good to remember. You start with the 64-bit plain message. So you take the plain text message, we put it into an IP, that's initial permutation. And at the end, remember, we will have a final permutation. It's the inverse of the initial permutation. So if that one takes the first bit, put it in position 8, this one will take number 8, put it in position 1. The exact opposite, or inverse. So now, but let's start with the permutation at the top. We do the permutation, there's no change in size yet in the data. And then we split it into 2 halves. We split the data into the right half here and the left half. And we only work on this right half. We pass it through a function. We'll see what the function later on. And when it comes out of the function, that's where the key would happen inside in there. And when it comes out, it's XORed with the left half, and it becomes the new right half. And that's right, the original right half becomes the left. We swap. And we do the same thing again. But inside there's an operation that happens using one of the keys each time, the 16 keys we generated. We do this 16 times, and at the very end, we put them together and permutate them one more time. to bring, you know, an inverse kind of permutation. So each iteration, we take the right 32 bits from the previous results and make them the left 32 bits, the left half basically, and we XOR the left bits of the previous step. So we do an XORing. So we look at it in a bit more details now. So here's the function that we will be working on. The right key, the new right key, the next right key will be the first key with the function. We'll have a function that uses the right half with the key, and whatever comes out of that is ORed with the left half to make the new right half. Let E be such that 48 bits of its output written in 4 blocks of 6 bits each are obtained by selecting the bits in its input in order according to the following. So first thing here, we first expand each right half. Remember, we have 32 bits of data. We want to expand it to 48 because the key is also 48. The right half is only 32 bits. We're going to make it a little bit bigger to 48. So we pass it, we'll cause this selection a table called an E table. E table is an expansion table that will make the key larger or the data larger, expanded from 32 to 48. And here's the table. This E table will expand any number of 32 bits, will turn them into 48. How does it turn them? Because it will duplicate some of the bits. So if you look at this bit number 32, 32 is used twice now. Originally we only had 32 bits, but some of the bits are going to be duplicated. I don't know what other bits are duplicated. See, bit 21 and 21 is duplicated, 20 is duplicated, and 32 is duplicated, and so on. So it's just like you say some of the bits, take them twice and write them twice. See, bit number 4 there is used twice, once in bit location 5 and 1 7. Bit number 5 up at the top is duplicated into position 6 and 8. So we're using the same bits. Why? They just want to make this data bigger. They expand it. This is an E table, expansion table, that makes anything you feed into it, it makes it slightly bigger. Like the condensation table we had earlier on. So the first thing we need to do to encrypt, remember we had the data, 64, split it into 2 halves. We have the right half, it's 32 bits, expand it, put an expansion function, expansion function there. It will make it bigger from 32 to 48. Now OR it with the key. The key is 48. So that's exactly what we had. The key is 48. The E, the expanded or data, the expanded half is expanded like that. And now every bit is ORed with the bit underneath it. And there it is, or XORed. Is it ORed or XORed, guys? Are there any 2 ones? There are no 2 ones. Oh, there were 2 ones there, yeah. and they gave us the 0. So it's XORed. So that's the first step. I'll wait till you're finished, guys, talking. I have a sore throat. I can't speak over yours. So we have a 48-bit key that's ordered with the 32-bit half of the data that's expanded into 48. Now the two of them are XORed together, and they're still 48. Now we feed these into what's called substitution boxes. You know what a substitution box does? It will substitute. It will not permutate. This is where the substitution happens in DES. This is not transposition, this is actual substitution. So far we've been doing a lot of transpositioning, that's permutating, but now this is where we get into substitution. And just take my word for it now, we'll work out how the substitution box works. But your substitution box, you give it 6 bits, it generates 4 bits. So it's substitution and condensation box at the same time. But that's how substitution box work. So every 6 bits go into a box, into a function, and it gives you 4 bits. You collect all those 4 bits together, and they are 32 bits. They're the same as the original size of the half. See, the half of the block of data that we wanted to encrypt is 32 bits. We first expanded it in 48, operated on it with the key, XORed it with the key, and we still have 48 bits, but the original is 32. Now we reduce them. The S box reduces from 6 to 4, and there are 8 of them, so our 48 bits are actually substituted, but also reduced to 32 bits. So the same as the original block that we started with, 32 bits. We expanded it to 48, but now we are bringing it back down to 32. Finally, we have a permutation. We do one permutation onto it, and that's one step done on one half. This is what the function is. But the function is, you take half of the data, half a block of data, expand it, XOR it with one of the keys, and then use the substitution boxes to reduce it back to 32 before you finish with it, permutate it. And that's basically, if you do that 16 times, you'll end up with the new data. So, but now let's look at an S box. What's an S box? And this is something you need to know in detail. The S box. What's the S box? It's the S box. DES system is famous with these S boxes. And it's like a substitution function, like what they call a black box. You put something in it, you don't know how it works inside, but it gives you some output. You put 6 bits, it gives you 4 bits, completely different. They are not permutated, they are completely different. How does it work? And these 8 boxes came in the standard as well. They actually published the 8 boxes. And all that's in the box, all you see is a table of 4 rows and 16 columns. And each one of those is a box. I just put in the numbers on top of them, the number of columns and the number of rows, but they're not normally included. You only have those 4 rows and 16 columns. The numbers start 14, 4, 13. This is the exact box number 1. Oh, this is the actual standard. Stop, please, guys, stop talking. The S-box is simple. It's a binary system that works as follows. I want to see if there is any sheet with explanation. Yeah, here's an example. No. No. I should have gone for 0, right? Should have started with 0. 0 to 15. Okay, and these are the rows. Row 0, 1, 2, 3. And I'm going to fill it with numbers. Yeah. Anyway, so let's say you get this input. Remember, the bits come in about, I don't know, 48 of them. Let's say the first 8. Let's just take the first 8. 2, 4, 6. 2, 4, 6. Yes. Oh, you get 2 more. No. No, it takes 6 and reduces 4, right? Yeah. So every S box, it's 6 into 4. So it takes 6 and produces 4 bits. How does it work? Very simple. It looks at the first bit and the last bit. The first bit and the last bit, which is 0, 1, it looks at them as the row number 0, 1. And then it looks at the middle bits, the 4 bits are 1, 0, 0, 1. 1, 0, 0, 1. What number is that? 1, 0, 0, 1. That's the column. 1001 in decimal. Anybody knows what's that in decimal? 9. And 01 is actually 1 in decimal. So it's row 1. That's what this will translate into. Row 1, column 9. So you have to go there, row 1. That's the second row. Column 9. There it is. And the number in it is 11. So the result of this will give us number 11 in decimal. But what's that in binary? Anybody knows? It's 3, 8 and nothing, and 4, 2 and 1. That's 11. Does everybody know how to convert from binary to decimal? So that's 11. So anyway, this input will give us this output. So it's 0, 1, 0, 0, double 1 will give us the output 1, 0, 1, 1. Right, it will always take input of 6 bits, it will always produce an output of 3 bits. So, can you tell me what this input will give us? Let me make it easier for you. This 0 is 0, 0, this is 0, 1, this is 1, 0 and 1, 1. These are the rows. Like this is in decimal, but that's in binary. Just to make it easier. So maybe it's best if you create a table, if you write table, write it in binary. Because what happens if, for example, if this one is like that, and it's okay. Who's gonna have a go at this? Are you with me? Yeah. So what's that number? Can you tell me how you reach that number? Tell the others how you actually get. What's this reduced to? What's the result of this one? Okay. I'll tell you one more time, okay, and you work it out, or you know it. Okay, you take the first bit and the last bit, you put them together, and that's the row. So in this case, the row will be 1, 1, row number 3. So it's one of these numbers. But which one is the one that's defined by those 4 bits? So which column, which number is this in decimal? And it will be top there. Anybody knows what this number is? 0, 1, 0, 1. 5. So you go to column 5, which is this one here. So column 5 and row 3, that brings us to the number 4. So what's the output in binary? 0, 1, 0, 0. Perfect, yeah. That's 4. That's 4. Okay, everybody knows how this works? Simple, right? All right. So let me try this then. Who wants to take this? You want to have this? 1, 1, 1, 1, 1, 1. What's the result of that be? Work it out and tell me if it's right or wrong. Okay, and what's that? All right, there's some people still don't get this. Pay attention, just 2 minutes and you'll know it for the rest of your life. At least for the exam part. Any 6-bit number, you take the first bit and the last bit together, 1, 1. If you want to change it into decimal, that's number 3. But so it's row 3 or row 1, 1. So it's going to be one of these one of these numbers from the last row. Now, which column? It's marked by the inside 4 bits. This is 1111, which is 15, which is the last column. Column 15. So whatever last column in the last row, they meet at that cell 10. So you have to write 10 here, but if you write it in an exam, you write it in decimal, you say 10, it's not good. It has to be in binary. 1010. So that's 10. If you don't know how to convert, every location has a position. This has a position 0, 2, 4, 8. So 8 and 2 is 10. That's how you write that in binary. You know how to convert to binary? Okay, that's how to convert a number to binary, guys. In binary, every position has a value, just like our decimal system. Remember, in our decimal system, if I say 732, what does this mean? It means 700. This number here is worth 700. In this column it's 30, and in this column is 2. In binary, the first position is worth 1. The second position is worth 2, 4, 8, 16, 32, and so on. So if I say number 8, you put 1 here and 0, 0, 0. That's 8. Because this position here, 1 will have the value of 8. So if you have to convert number 10, you have to turn some of these 1s to make a 10. So 8 and 2 is 10. So you turn 8 and 2 is 1. The rest of them are zeros. So that's, okay, do you know how to convert now? Right, if you want to put the number 14, how would you put 14? It's 8 and 10 and 4, right? 8 and 10 is 8 and 2 is 10 and 4 is 14. So those numbers will have 1s, the rest everything else will have zeros. So this number here is actually 14. Okay, have you learned it? That's if you want to convert. You'll need to learn how to convert binary to decimal and decimal to binary. That's one way to convert small numbers from decimal to binary. If you have the binary number, you want to convert it, you just add the numbers together. Let's say this one here. This is how to convert from binary to decimal. You say the first number is worth 1. It's like this, or if I say to you, I give you 700 in our decimal numbers. That means I give you no 1s, no 10s, but I give you 7 of the hundreds, 700. In binary, if I say, right, what about this binary number, 1000? It means I'm giving you no 1s, no 2s, no 4s, but I'm giving you 8s. So it's 18. So this equals 8. So all you have to do is add the numbers that have 1s in them. So what about this number? This number I'm getting no 1s, I'm getting 2, I'm getting no 4, I'm getting 8. 8 plus 2 is 10. So that's how to convert it into decimal. If you have the binary. What's this binary here? You say no 1s, but 2, 4, 8. So 4 and 2 and 2 and 4 and 8 is 14. All right, that's something you need to practice. But that's not really important to me, but you should know it. What's important to me is this one. Now, convert this number. Okay? Don't know what this for is? What's this value? Which row and which column? Okay, everybody got this? Oh, 6, 5. Sorry. Okay, column 6 is 5. Column. I'm gonna just fix these. This is 15 here. This is 14. This is 11. This is 10. 9. So guys, for this one here, you take the first bit and the last bit, and they make the row. So it's row 0, 0.
And see, we can sit down where you're writing.
Okay. Okay, so those, we take the first bit on the left and the first on the right, and they make the row. So it's 0, 0. So row 0, 0 is the top row. Now which column? You take the 4 bits in the middle, 0, 1, 1, 0. That translates into 6. 4 and 2 is 6. So that's column 6. So row 0 and column 6. Column 6, they meet at the number 5. So you have to write 5 in binary. What's 5 in binary? I have a volunteer here. Yeah. So 0, 1, 0, 1. It's 5, but you cannot 5. 5 is 1, 0, 1. But the output has to be 4 bits. If you put 3 bits, you don't get the mark. S-box must produce 4 bits. Even if it produces, okay, let me get you another number to work. All right, so it's 0. What's this outcome here? Please work it out, everybody. And give me the result in binary. If I was given the pens today, you'd get it. I have a few pens to give away, guys. Go for them specifically, but oh, look at the good ones as well. All right, so everybody got this S-box operation. If you're asked to design a box, which we got this maybe last year or the year before, question. Hey, design your own S-box. What you need to worry about when you're designing the box, of course, the number of rows and number of columns. But you could change that. But see the number in the middle. The number in the middle has to be a number, in this case, that only consists of 4 bits. So every number in the middle here can only be written in 4 bits, no more. So the largest number, the biggest number you write in 4 bits is 1111, which is 15. So inside that box, the largest number can be 15. You can't write number 16 or 17 inside of that box. Because if you're asked, unless if you're asked, design an S box that gives me S and 5, well, in that case, the numbers will be written in bigger. So it depends how many bits are to represent the outcome of that S box. For example, here's an example. If I say design an S box, that takes 5 bits and produce 3 bits or 4 bits, 3 bits. An S box that takes as input 5 bits and 3 bits, based on the S box idea. The S box idea, you need the first bit and the last bit to tell you the number, the row numbers, and the middle ones will give you the column number, and the numbers inside, they must be, yeah, they must be 3 bits long. So in this case, our input has to be, for example, 5 bits, let's say 1 and 1, and inside, well, this one didn't specify the rows, number of rows. So, you know, normally in the question it'd be asked, I need maybe 2 rows or 4 rows or 6 or 8 rows like this one here, or 16 rows. Let's go for 8 rows. So if you're asked for 8 rows and 4 by 8, that means these 2 bits will indicate the rows. So the table has 4 rows. That's 0, 1, 2, and 3. And the number of columns 8. That means how many? What's the largest number you can write in 8? 0, 1, 2, 3, 4, 5, 6, 7. No more. So this is the only table we're going to need to have. So the number of rows like the first 2 bits will tell you how many rows, and the first middle bits, let's say you need 3 bits in this case. Yeah, so it takes 5 bits. So those 3 bits will tell you, see, in 3 bits you can write any number between 0 and 7. So this is the kind of thing, that's the design that you might need to come up with. So number of rows is 4 based on those 2 bits. Those 2 bits give you the row, and those 3 bits will give you the column. And you can have a maximum of 8 columns using 3 bits. The inside number, it depends. The inside number, if they say to you, it has to give us an output of 3, that means the biggest number is 8. If we say output of 4, that means the biggest number in there is 15. Okay, let's say, just say 3. Inside, the output has to be 3. That means all the numbers in here must be represented only in 3 bits. The largest number you can represent in 3 bits is 7. So this can be 7, 6, 5, 4, 3, 2, 1, 0, 7. No, you can't write 9. Write 9 will need 5 bits or 4 bits to represent. Okay. Anyway, so you fill any numbers from 0 till 7. And then you might be told, okay, what's this number out of your box? What's this number here as input? Having this input, what's the outcome here? This is input. What does this give us? So first you take that bit and that bit, give you row 0, 1, which is this row here. In the middle, columns 4, 2, and 6. So 1, 2, 0 equals 6. So that means column 6, right? Yeah. So this column here. So now we are in row 0, 1 and column 1, 1, 0, which is 6, and that meets at this point here. So the outcome is 3 in decimal, which is in binary 1, 1, right? The outcome has to be 3 bits, 0, 1, 1. Is that okay? No, you work this out for me. Okay, you work out this last one. What is this in binary? In this box. Remember, this is based on S box, but here this is a different S box. Your own S box. All right, whoever gets this one first, who got this? Okay, too late to I was gonna produce the pen, but next time. The next one. Right. No, now I leave that for Hill Cipher. I give this for this one. All right, let's go back to the slides, and then I give you one problem to work out. And the first to get it will get a pen, and then we all go home. And I'm gonna close something else. I do the attendance because I have to leave now. Is the attendance, everybody okay with the attendance? Anybody has a problem, put your hand up. Because if I close it now, I'm not opening it again. Everybody is okay there? Anybody did not get their message? Yeah, what's your name? Okay, first character. A. It's okay now, yeah. Everybody okay? Right, save attendance. Whew. So I'm going to close that soon, so that's finished. All right, these are the real S boxes. Sorry. These are the actual S boxes that came in the standard, right? So if you're a programmer, these are the actual real S boxes. That's exactly the numbers they have in there. S box 1, 2, 3, 4, up till 8. Right, and this is the technique how to use it. Finally, there's a permutation. So, in general, guys, this is the inverse permutation. Remember to encrypt the data first, permutate it, and then at the end you do the opposite of that. And this is it. These tables are in the standard itself. So this is the inverse, that's the power of -1 of the initial permutation. The first permutation we had, this is the opposite. The reversal of that. All right, let me see if there is an S box. Okay, using this S box. All right. The first to get me the right answer, they get this pen. Put your hand up first. What's the number? Okay, what's the result? Okay, let me make sure I'm getting the right one. 100, that's 18 decimal, right? You got 18 decimal. Anybody else got the number? What's that in decimal? Okay, I got two different numbers. Hold on. 1 and 0. Remember, this is 0, 0. 0, 1, 1, 0. So we are talking about this column here. Okay. And now we're talking about here 5. That's 0, 1, 2, 3, 4, 5. That's the number 8. Okay, guys. Have a good weekend. Well, we'll see you Friday. I'll be placing, I don't know if I placed them. I'll put practice questions, read them, study them. You don't have to do the work for me, do it for yourself. You don't get marks for it. But then I'll put a tutorial, that's the one you must submit. and you get marks for it.